Okay, so we've been having a little bit of fun with objects sliding down inclined planes, and we've talked a little bit about weight and normal force and force of static friction and force of kinetic friction, and now we're going to add one more complication, and that's an applied force. So we're going to exert a horizontal force on the block. Okay, and what we're going to discover, we've got some intuition now, we've got some understanding of how to think about the physics of the situation. This will add a great deal of richness, and then we'll actually work through the math, and in the end, we will discover something that probably none of you would have expected. And this is exactly how discoveries in physics work. So it's a super cool example. Okay, it sort of like really deepens our understanding of the physics and shows us something new. Okay, so the idea is something like this. Again, it's all very simple. In physics, what we try to do is understand as deeply as possible very simple situations. Okay, so here we've got the incline, and if our angle is below the static, the critical static angle, then it doesn't accelerate. But we keep on cranking up the angle more and more and more, and then eventually we reach the theta static angle, and the block begins, static friction is broken, and the block begins to accelerate down the incline. So what we're going to assume is that we are putting the angle greater than theta static, so that automatically it just begins to accelerate down the incline when we let go. Okay, and then what we're going to do is we're going to prevent it from sliding down the incline. So the force of static friction, when the angle is too high, the force of static friction is only limited, and it's not enough to keep it from sliding. So we're going to help it by applying a horizontal force, and part of that force is right along the incline, helping the force of static friction. Okay, keep it from sliding. So I'm past the static limit. And the question is this: if I apply a horizontal force, great, I can keep it from accelerating down the incline. But if I reduce the strength of that horizontal force more and more and more, eventually it will break the static limit and it will accelerate down. So the question is, what is the minimum horizontal force I need to apply when the angle is cranked up high to keep the block from breaking static friction and accelerating down the incline? And then we're going to answer sort of a directly related question, sort of the flip side, is it's clear that if I push hard enough in the horizontal direction, I will exert enough force in the upward direction that I will break the static limit in the other direction, and I can make this block accelerate up the incline. Okay, by pushing hard enough horizontally. So then the question is, what is the maximum horizontal force I can apply before it begins to slide up the incline? So there's minimum force before it slides down and maximum force before it slides up. So this is a very typical sort of Phys 121 type problem, a minimum maximum type problem. Okay, and it's a great example. So if you can, work through, understand the physics of this problem and work through the math, you're doing really well. Okay, so here we have our inclined plane, and we've tilted it up past like pretty steep. And so the angle here, theta, is greater than the theta static limit. So if we put a block on here and do nothing, it will break static friction and it will just accelerate down. But then what we're going to do is make it a little bit more interesting. We apply a horizontal applied force to the left like that. And the question is, what is the magnitude of the applied force? What is the minimum magnitude of the applied force to keep it from sliding down? And at the same time, we'll solve both problems at the same time. I'll show you some efficiency in how you work with equations. We'll also ask, what is the maximum applied force I can apply before it accelerates up? Max before it accelerates up. Okay? And so we've got some intuition, we've got some skill with adding up vectors tip to tail, showing the net force. Now, in all of these examples, minimum and maximum, we are assuming that the block stays static. Okay, there's no acceleration. We're taking it to the brink of accelerating down and to the brink of accelerating up, but it's still static, which means that whatever forces are acting, they better all add up to be zero. Okay, so that's how we're applying Newton's second law. And we're just going to do it with just drawing vector diagrams, okay? And you'll see it's kind of cool. Okay, so the first case we'll look at is the minimum case. Okay, so minimum. So for the minimum case, it looks something like this. We're gonna draw a dotted line, which represents our inclined plane. Let me go about that size, because I want to draw another one down here. Okay, and so then we say we want to add up all the forces. What are the forces that are acting? Well, the field force. Well, gravity. Gravity is pulling down, and the strength of the gravitational force, the weight, is just mg. So we have mg, force of magnitude mg, the weight pulling down. I want to draw this diagram carefully so it works out nicely. Okay, so this is the weight pulling down. And then what we're going to do is we're going to next add tip to tail the applied force, which is a horizontal force. So weight plus applied force. Let me just draw it right about here, this long. Okay, so we have an applied force. And yeah, let's call that the applied force. Okay, and so weight plus applied force. And then, but there's also going to be a normal force, because certainly there's a component of the weight in that direction, and there's certainly a component of the applied force in that direction. And so that's going to compress these atoms, and they're going to try to spring back. So there's going to be a normal force in that direction. Okay, so that normal force, weight plus applied force plus normal force. And let me do this nicely. And that comes up to here. Okay, because we know that the last force is a force of static friction. So we're trying to prevent the block from sliding down. So the force of static friction is working as hard as it can to push up, to keep it from sliding down, to keep it static. Okay, so the force of static friction, we go weight plus applied force plus normal force, which is perpendicular to this dashed line, plus force of static friction. That's the force of static friction, which is tangential to the incline. Okay, so those are our four forces, and we've drawn them in such a way that they all add up to 0 because we're assuming the situation is static. Okay, and so that's certainly true. If we apply some amount of horizontal force, then there will be a certain amount of static friction required to keep that block from breaking static friction and accelerating down. But now here's the interesting thing. Maybe I'll try to get a different color here. Maybe that'll help. Okay, so now what we do is we say, well, what happens to this picture if we reduce the applied force? Remember, we're going to go smaller and smaller and smaller applied force until all of a sudden static friction breaks and it begins to accelerate down. So if we reduce the strength of the applied force and make, instead of that long, we make it shorter, like that short, then the normal force becomes this guy over here. Let me actually draw it as that's the normal force now. So the applied force is now shorter. The normal force is now like this. And you'll notice something important. You'll notice that as you reduce the applied force, the force of static friction has to get longer, has to get larger. Okay? And let's suppose that we've reduced it to the point where that force of static friction is now the maximum allowed force of static friction. So in orange here, I will write this is now Fs max, and this is now applied force minimum. Okay? So that's kind of cool. So that's one diagram that we can look at and think about. Now let's look at the other case, where we're going to apply a really strong horizontal force. If we apply too strong of a horizontal force, there's too much of an upward component, and it will break static friction in the other direction, and it will accelerate up. So now we're looking at the maximum applied force that we can apply. Okay, and so we draw a similar diagram. Okay, so down here we have this this dashed line indicates the plane, the inclined plane. And now let's start drawing our forces. So we play the same game. Let me just, again, make it nice. Okay, so the weight is the same. So the weight is like this, coming down. That's a force of magnitude mg coming down that we know. And then what we're doing is we're applying not just a small applied force, we're applying a really large applied force. So weight plus applied force is now long. Let me just sketch this out here. Think about this. Take it down to there. Okay. So that is our applied force. Okay. So weight plus applied force. There's certainly, again, a normal force. And so that normal force, remember, is always in a direction perpendicular to the incline. So it'll come up to here, and be perpendicular to the incline. That's supposed to be perpendicular. Okay, and so that's the normal force. But now we need one more force to close this shape, so that the net force, the sum of all the vectors, the vector forces tip to tail, adds up to 0. So weight plus applied force plus normal, and now this is the static friction force. Now you'll notice something very interesting. First of all, when the applied force is small, then the block wants to slide down, and to keep it from sliding down, static friction adjusts itself as hard as it can that way up the incline to keep it from sliding down. That's this case. However, when we're pushing really hard like this, the block will eventually want to start going up. And so to keep the system static, force of static friction will be pushing down to oppose the motion. So if it wants to go up, the atoms in the bottom of the block are pushing against the atoms in the top of the incline, pushing them that way, shifting them that way. They're like on springs, they push back like this. The force of static friction is now down. You see it's coming down like that. Okay, so that's great. So this is for a large horizontal applied force, but everything still remains static. So then we ask, well, what happens if we really sort of crank it up? If we make the applied force larger, so again, I'll go in a different color here. So let's make the applied force even longer, bigger in magnitude. Say, let's make it this big. Okay. Then the normal force changes to, it's greater in length, okay, and it ends up being over here. Now the normal force looks like this. And so now the force of static friction required, because you're pushing so hard now, the force of static friction required to keep it from accelerating up is now longer. It used to be this long. Now, by increasing Fa, you've made it this long. Okay? And so let's suppose that you've cranked up how hard you've pushed sideways so that you are now at Fa maximum. And that corresponds to this force of static friction being maximum. Okay, so those are the two diagrams. Okay, and so in one diagram, force of static friction pushes up to keep it from sliding down. In the other, it pushes down to keep it from sliding or accelerating up. Okay, great. So those are our basic intuitive picture of what's happening. Okay, and now what we want to do is actually do some math and solve the problem. What is Fa minimum and what is Fa maximum? And in this case, it really helps you can work with these diagrams as well. And, these are angles theta, and so when I work everything out straight from this diagram. But in this case, it tends to be a little easier to actually introduce a coordinate system and split these four forces, weight, normal, force of static friction, and applied force into x and y components. So I want to illustrate, because that's a really important skill too. So I want to illustrate how it is you would do that in this case. Okay, so the first thing we do is we draw a free body diagram. And so the free body diagram, what we always do is, at least before we do rotation and so on, we just treat the object that we're interested in, its dynamics, we're interested in that object, we treat it as a point particle. Okay, and so we draw just a dot there, and we label it with the mass. And then what we do, which the mass doesn't matter in the case of, well, I guess it matters in terms of the weight. Okay. Anyways, so we indicate the mass there, and then we put in a dashed line indicating the angle of the incline. Okay, so this angle here is theta. And then we start adding forces. And remember that all of the forces that are exerted on M, we draw the base of the vector at M, and so that it goes this way, or it goes this way, it goes this way. They're always going in an outward direction, and we add them all up. Okay, so the one force that's really clear is the weight. So the weight is pulling down. Okay, again, I'm trying to draw this carefully. There's the weight pulling down. And then the next force, we can just add them in the order here. The next force we added was the applied force. The applied force is to the left, like this. So there's an applied force. Okay, and then there's a normal force, and that normal force is perpendicular to the incline. So it's in that direction. And then the force of static friction, and this is the tricky thing, the force of static friction in the minimum problem points up. the force of static friction in the maximum problem points down the incline. So it's that way or that way. So we're going to draw the diagram as if we're dealing with the minimum problem. And then we'll do a little trick with plus minus signs to, at the same time, do the maximum problem. So drawing it for the minimum problem, the force of static friction is pointing up the incline. Okay, so that's the force of static friction. Okay, so that's our free body diagram. And then we can identify some angles here. And so one nice way to help with the angles is to make that angle theta either significantly bigger than 45 or significantly less than 45, so that you can just look at angles and say, ah, yeah, theta is the angle that's significantly bigger than 45. Okay, so I'll just label a couple of angles here. So if we go down like this, this angle here is less than 45, this angle is bigger than 45, so that angle is a theta. And similarly, this angle is bigger than 45, so it must be the theta. So just put in a couple of thetas, because you're going to be looking at projections of these vectors along I hat and j hat, or x and y directions. Okay. Now here comes the really important thing. Okay, so this is a minimum maximum problem. And so what we're doing is we are going to write down eventually this equation. So the main equation is trying to figure out where to write this. Where is this going to work? Let's put it up here. The main equation is that the force of static friction, okay, we don't know what that is. We have to solve. We have to add up all these forces and set it equal to 0. And that will allow us to solve for the magnitude of the force of static friction that's required to keep things static. So we don't know what that is, but we do know that it must be less than or equal to Fs maximum. Okay? And Fs maximum, we don't have a formula for Fs, but we do have a formula for Fs maximum. And that's equal to mu s times the normal. Okay, this is the crucial equation. Okay? We're going to solve for some stuff and plug it into here, and that less than or equal sign, that inequality, is going to tell us, you know, the force, the applied force must be less than or equal to this, which is Fa minimum, greater than or equal to such, which is Fa minimum, or less than or equal to such, which is going to give us Fa maximum. Okay, so that inequality sign is really, really important. So the crucial thing is this, and I'll say this again and again and again, you don't know what F is, and you don't know what N is. What you have to do is write down some of the forces as mass times acceleration equals 0 in this static case, and then solve for those two unknowns. It's a two-dimensional problem. You have two equations. You can solve for those two unknowns. You plug them into this equation, and then F applied will be somewhere in those equations, and then that will give you the inequality. Okay, so that's what we need to do. So how are we going to do that? So one really, really important sort of point here is remember that we can choose I hat this way and j hat this way. We can choose the orientation of the I hat, j hat unit vectors, of the x and y components of the vectors, any orientation we want. We could choose like this, or we could choose like this. Okay, so if we choose like this, then what we find is, so horizontal and up, then we find that the weight has pure x or y components. The weight and the applied force have pure I hat and j hat components. This has only, you know, I hat, and this has only j hat. But then these are mixed. So your equations, you'll have two equations, and if you choose your I hat and j hat this way, one of the equations will have, both of the equations will have both N and Fs. They'll have both the magnitude of the normal and the magnitude of the static friction force, and you don't want that. What you want to do is you look for what you're trying to solve for. I'm trying to solve for the length of that vector and the length of that vector. So why don't I choose my I hat and j hat like this? Okay? So that my I hat equation, maybe this is I hat, so my I hat equation has only the normal and not Fs, and my j hat equation has only Fs and not the normal. It becomes one equation. You have two single equations and single unknowns, super easy to solve, as opposed to two equations and two unknowns where you have to do substitution and multiply by coses and sines and this and that. Okay, so so we're going to be clever about this. You know, think about things carefully. And actually, I chose in my notes here to choose to have I hat down like this, down the incline. So that's I hat, and then j hat is perpendicular to the incline. Yeah, just so that I don't mess up the signs. Okay, so we got that. Okay, so that's great. And then we say, okay, in the case of the minimum problem, let me put that over here. In the case of the minimum problem, what's happening here? In the case of the minimum problem, we know that the force of static friction is up, trying to prevent it from sliding down. Okay, and so Fs, the vector Fs, okay, is going to be, how do I want to write this, is going to be in the negative I hat direction, and has a magnitude Fs. Fs, without the vector on top, is the magnitude of the vector Fs. So Fs is a positive number. Okay, and so this vector is in the negative I hat direction. So that's appropriate for the minimum case. For the maximum case, we have that the force of static friction vector, okay, is going to be pointing down. Everything else will stay the same. We'll have a weight, applied force, normal force, but we're pushing really hard now. It wants to slide up, so the force of static friction is pointing down to prevent it from sliding up. Sliding up. So now Fs is in the downwards direction, which is the positive I hat direction. So it's positive, the magnitude of the force of static friction times I hat. Okay, so we can solve both the minimum and the maximum problem just by having a minus or a plus sign, just changing the sign. Okay, so great. Okay, so now let's write the I hat and j hat components. So we're going to basically add all the vectors up, of all four vectors up, and we're going to set that equal to 0. And we'll do that first with the I hat components and then the j hat components. Okay, so we're solving Newton's second law here. Sum of the forces is mass times acceleration, which is 0. So we look at the I hat component. So all of the vectors, let's look at this component of the force. Okay, so so this weight has a component of force in the I hat direction, and it also has a component of force in the negative j hat direction. We're interested in this component of the force. Okay, so that side of that triangle. Okay, and so this angle over here is the angle that's greater than 45, so that's a theta there. And so this side of the triangle, the I hat component of the weight, is going to be W times sine theta. Okay, so it's positive W sine theta. That's the I hat component of the weight. Now let's look at the I hat component. Which one do we want to do next? Let's look at the I hat component of the applied force. So I hat is this way, and so the I hat component of Fa is the projection of Fa along this direction, but make it negative. So just take Fa times cos theta, that's the projection along here, and then make it negative, because I hat is that way. So it's negative the magnitude of the applied force, so Fa without the vector on top is the magnitude. Okay, multiply that by cosine of theta. Okay, which one do we want to do next? Let's do now the force of static friction. So in the case of the minimum problem, the force of static friction is that way, so it's opposite to I hat, and so it's negative the magnitude of the applied friction force. In the case of the maximum problem, the force of static friction is that way. It's in the positive I hat direction, so it's positive the magnitude of the force of static friction. Okay, great. And so when we write a minus sign on top of a plus sign, it means that so throughout all of these equations, the upper sign refers to the minimum case, the lower sign refers to the maximum case. But you can just treat that minus plus just as an algebraic thing. If you multiply by minus sign, it becomes a plus minus. Okay, so upper sign is minimum, lower sign is maximum case. Okay, so anyway, so this is the net force in that direction. Well, the net force in all directions better equal to 0 because this is a static problem. Okay, and then we look at the j hat or y component. J hat is this way. Okay, and so we're looking for the projections of all four vectors in the positive j hat direction. Okay, and so let's see, let's look at the weight first. So the weight is this guy. It does have a component along this axis, but it's in the negative j hat direction. So it'll be negative the magnitude of the weight times weight times cos theta. So if I take the hypotenuse times cos of that angle, I'll get that projection of the weight. Okay, and so it's in the negative j hat direction, W cos theta, weight times cos theta. Okay, and then we look at the applied force. So here's the applied force. It does have a component in the j hat direction, so that's that direction, but it's in the negative. So it'll be a negative. Take the magnitude of the applied force, Fa, okay, and this angle here is the complement to theta. So this angle over here, let me see, that's the complement to theta, so that's theta. Okay, so if you take, we're interested in this j hat projection, so that's the hypotenuse. So times cos theta will give you that, times sine theta will give you that, which is what we want. So it's minus Fa sine theta. Okay, so just work slowly and carefully and make sure you don't make sign mistakes. Okay, so that's that. And then the last one we want to look at is the normal force. So the normal force has a j hat component. In fact, it's exactly in the j hat direction. That's in fact why we chose I hat and j hat, so that the normal would lie along one axis and the force of static friction would lie along the other. So the normal force is in the plus j hat direction with full magnitude. Okay, and that's the y hat component of all the forces, and that better also equal 0. Okay, so now I want you to look at these equations quickly, and remember what we're trying to solve for is what's the magnitude of the force of static friction required to keep the thing static, and what's the normal force. Okay, we don't know those things. Well, now we do. We solved Newton's second law. By solving both of these equations, we've solved Newton's second law, and then we can solve this equation trivially for Fs, because this equation involves only Fs and not n. And we can solve this equation trivially for n and plug it into there because it involves only n and not Fs. If we, as I said, if we had chosen the axes like this, we'd have a mess. This equation would have both Fs and n in it, and this equation would have both Fs and n in it. We'd have two equations and two unknowns to solve. So try to think carefully about how you set up the orientation of your axes. Okay, great. And so then all we do is, the solution to this is trivial. We just plug it into there. So on the left-hand side, we want Fs. Well, what is Fs? So on the left-hand side, Fs, if we solve for Fs, take Fs to the right-hand side. That means change its sign. So we have plus or minus Fs is equal to this chunk. So that means that Fs is plus or minus this chunk. So weight times sine theta minus applied force times cos theta. So this is Fs when we solve this equation. Okay? And then we say, there's an inequality there. Make sure you put that in. That's less than or equal to mu s times the normal. What's the normal? Well, Newton's second law tells us that the normal, bringing the normal to the other side, or bringing this chunk to the other side, the normal is the negative of this chunk. Okay, and so it's negative of negative is positive, so it's W cos theta, positive, that negative, negative both become positives, positive Fa sine theta. Okay, remember, be careful with your signs. Okay, so that's that. And then one final thing I'll say is, this is not completely necessary, but when I look at this thing, I would say, well, you know what? Those critical angles for theta static and so on, those critical angles are tangents of theta. So here we have sines and cosines. We can convert this equation into an equation involving just tangents of the angle theta by dividing both equations by cosine of theta. Okay, so if this is less than or equal to this, then this divided by cos theta is less than or equal to this divided by cos theta. When we divide the left-hand side by cos theta, both terms are divided by cos theta. And so we get a plus minus W sine divided by cos is tan theta, which is the slope of the incline, minus cos divided by cos is 1. And that should be less than or equal to mu s times cos divided by cos is 1 plus Fa times sine divided by cos is tan theta. Okay, so we have that. And let me see. Yeah, now we want to isolate Fa. And so let's put everything involving W on the left-hand side. So we're going to run out of room here. So let's start down here. So let's take W, bringing everything involving W to the left-hand side. So there's a W times plus minus tan theta. And there's a W on the right-hand side. We pull it to the left-hand side, it changes sign. So it's minus mu s, and that's it. Minus mu s. Did I forget about the plus minus sign? I did. Oops, sorry. So W, there's a plus minus tan theta. Plus minus here. Plus minus tan theta, and then minus mu s. And that should be equal to that should be less than or equal to, bring everything multiplying FA to the right-hand side. So that's going to be FA times, I'm going to write this in a nice order. So FA times on this side, there's going to be there's a minus times plus minus is minus plus. Bringing it over to the other side is a plus minus. So it'll just be plus minus 1 times FA, and then there's an FA on this side, which is positive mu s tan theta. So it looks like that. And so at the end of the day, what we're looking for is solving for FA. And so then the final answer here is, well, actually, let's leave it in this form for now. Okay. So that's our main equation here. Okay, now we're going to look at these two cases, and we're going to see, we're just going to think about them, and they're kind of interesting. Okay, so for the minimum case, I think we're definitely going to run out of room on this board. So for the minimum case, what we're looking at is the upper sign. Okay, so in this equation, we just take the upper sign. So minimum means the upper sign, and then we solve for FA. So this is saying that FA is greater than or equal to this chunk divided by that chunk. So FA is then greater than or equal to this divided by this, okay, with the upper sign. And so that becomes tan theta minus mu s, that's in the numerator, times the weight W, divided by, choosing the upper sign here, 1 plus mu s times tan theta. And so that's our answer. Okay, so for the minimum problem, we're asking, what is the minimum force I can apply and yet still not break static friction? So it's saying that in the minimum case, the applied force must be greater than or equal to this thing, which means that this thing is equal to FA minimum. Okay, so if you apply a force equal to that or bigger, this thing will not slide down. Okay, so that's your answer. And then you think about this a little bit, and so there's a couple of cases that you want to look at. So one of them is when theta is actually equal to theta static. So we started with theta bigger than theta static, but now we can crank theta down until it becomes just equal to theta static. So in that case, when theta is equal to theta static, okay, we just think about this for a second. If theta is equal to theta static, okay, so that means we have cranked it up like this just before it slides, which means that we don't have to apply any force to keep it from sliding down. So the answer should be 0. Well, let's see if that's the case. If we put theta equal to theta static in this formula, well, we have tan theta static. Well, tan theta static, that's the slope, that's the critical slope, that's equal to mu s. And so tan theta static minus mu s is 0, and that's right. Correct. Okay? And then we can consider the other case, if theta is bigger than theta static, which is the case that we're normally looking at, we crank it up to be bigger than theta static, and then you can see, well, tan of an angle bigger than theta static will be bigger than mu s, so this minus this will be positive, and the applied force is some positive number. So this is greater than 0. So that makes sense as well. Okay? And then we can take a particular example. Okay, so because that's the beauty of working just algebraically. It's a super good thing to be able to do. So by the time you get to second year, you know, it's all algebraic, right? So I'm trying to like get you guys going in that algebraic direction. Okay, so it's just so much more powerful because now we can look at a cool case. We can say, well, what happens if we crank the angle right up to 90 degrees? look at that. I'm applying a force, it's a sideways force, and it's not breaking the static limit. So there must be a solution to this equation when the angle of the incline is 90 degrees. Okay, so let's plug that in and see what happens, and see if it makes sense. So the example now is, let's look at theta equals 90 degrees. The incline is vertical. So in that case, the minimum required horizontal force to keep things static is equal to what? I don't know, let's see. So when we set theta equal to 90 degrees, then tan of theta, the slope, becomes infinite. So as we approach 90 degrees, this number becomes bigger and bigger and bigger. And it's certainly mu s is something like of the order of magnitude 1. And so it's negligible. So we can ignore negative mu s in the numerator. In the denominator, we have mu s times tan theta. Well, that's approaching infinity, which is way bigger than 1. We can ignore the 1. So really, when theta approaches 90 degrees, the numerator is tan theta and the denominator is mu s times tan theta. This is a little bit of sort of calculus reasoning. So then you cancel out the tan thetas, and it's 1 over mu s times the weight. So it's the weight divided by mu s. Okay, that's what FA minimum is. And then you ask yourself, well, does that actually make sense? So let's just draw a picture. What this thing is saying is the following. This is a super important step. Who cares about that? You have to see that it makes sense. Okay, so now we've cranked the incline up to 90 degrees, and we have a block sitting here like this. And what I'm doing, it's saying that I need to apply a force of magnitude W over mu s. Okay. Notice that the smaller mu s is, the stronger, the more slippery the surface is, so to speak, the harder you have to push to keep it from sliding down. So when mu s gets small, this force gets large. Okay. Also, when the weight gets large, then the sideways force also has to be large. So all of this is making sense. Okay. If you push hard like this into that block, well, then that block will be pushing hard into that inclined plane, and it will be bending the inclined plane like this, compressing the molecules. They'll spring back that way, and there will be a normal force in that direction. And so that normal force is like this, acting on the block, is of exactly equal magnitude but opposite direction. So the normal force will equal also the weight divided by mu s. That's great. Applied force, normal force. And then we say, and then what is Fs maximum? Well, the inclined plane is exerting an upward force. This thing wants to slide down. So the inclined plane is exerting a static friction force up to try to prevent it from sliding down. And it's reached the maximum allowed static friction force. Okay, so that's a static friction force that's applied to the bottom of the block in that direction. And so we are at Fs maximum here. Well, what is Fs maximum? Fs maximum is mu s times the normal. So that's equal to mu s times the normal. Well, what's the normal? That's the weight divided by mu s. Weight divided by mu s. The mu s cancels, and it's the weight. Well, that's interesting. So it's saying that to keep the block from accelerating down, the force of static friction is exactly equal to the weight. And that makes perfect sense because the last force we have to add is the field force, which is gravity, which is the weight. And so you can see that the horizontal forces applied and normal cancel, and the vertical forces, weight down, static friction force up, exactly cancel as well. All the forces are balanced, and this thing remains static, and that's exactly this situation right here. That number, weight divided by mu s, is exactly how hard I'm pushing right now. If I push any less than that, static friction breaks, and the thing starts to accelerate down. Okay, so that's cool. But now, the last part here is even more cool. I think we're going to run out of space. I gotta erase this stuff. Okay, so the last case, and I think that we can get rid of this kind of stuff here. We can get rid of these equations. We've already solved those equations. Really, the only equation we want to keep is that one. This was just part of solving the equations. Okay, we want to keep this thing, and let's erase the minimum case. Okay, great. We've got a bit of room now to do the maximum case. All right. So the maximum case, what do we want to, let me just do it up here. So for the maximum case, we had an upper and lower sign. For the maximum case, we're using the lower sign in this equation. Remember, we were efficient and we solved the equation for both the minimum and the maximum case. Now we just look at this equation and use the lower sign. Okay, so if we use the lower sign, it's going to look like this. It's going to be weight times, the lower sign here is negative tan theta minus mu s, and that's less than or equal to the magnitude of the applied force, minus, the lower sign is minus there, plus mu s times tan theta. Okay, great. So you'll notice that there's a whole bunch of minus signs in this equation. And so to get rid of all those minus signs, or 3 out of the 4 minus signs, 3 of the minus signs, we multiply the entire equation through by -1. Okay, so so that means every term, if this is less than or equal to this, then -1 times this is less than or equal to -1 times this, or actually greater than or equal to -1 times this. So let's multiply the entire equation through by -1. So it becomes weight times positive tan theta, positive mu s. Okay, and the important thing is that when you multiply an inequality by a minus sign, this inequality flips. I'll tell you why in a second. Give an example why in a second. Fa, that minus becomes a +1, and that plus becomes a minus mu s tan theta. Okay, and so just to sort of explain the flip in that, that's important, to flip in that inequality. If this is less than or equal to this, suppose that equation read -2 is less than or equal to, I don't know, 1. That's certainly true. If we multiply this equation through by a minus sign, the -2 becomes a +2, and the 1 becomes, +1 becomes a -1. Well, in this case, you have to flip that because it's not true that 2 is less than or equal to -1. You have to flip this guy. So it's 2 is greater than or equal to -1. So that's why that inequality flips. And then you look at that and you say, well, that makes sense, because in the minimum problem, we wanted an equation that said the applied force is greater than or equal to something. Now, in the maximum problem, we want to say the applied force is less than or equal to something. So here the applied force is less than or equal to this junk divided by that junk. Okay, so let's crank that out. So we get that the applied force now is less than or equal to this over this. So that's tan theta plus mu s divided by 1 minus mu s tan theta, and times W, times the weight. Okay, so that's our expression. So it says that we're pushing really hard sideways now, hard enough that it's almost going to slide up. So force-static friction is really pushing down hard. And so it says that the maximum applied, the applied force has to be less than or equal to this, which means that this is equal to Fa maximum. Okay, and that's our main result. And now we're going to look at this thing, because this is actually a really cool result. Okay, and we're going to need a little bit of room to work on that. We don't need this equation anymore. Okay, so let's see what this thing is saying here. So the interesting case to look at is this denominator. Normally this denominator is positive, okay, and so you just have the applied force is less than or equal to some number, okay, and so that's your maximum applied force. But what's interesting is that because there's a minus sign there, it means that this denominator could become equal to 0. So normally it's positive, but as you crank up the angle more and more and more, that gets bigger and bigger and bigger, and you could get 1 minus a number just a tiny bit less than 1. This becomes a smaller and smaller number in the denominator, so the applied force becomes larger and larger, and when this mu s tan theta is equal to 1, then this number becomes infinite. Okay, so let's look at that special case. Okay, so when the denominator approaches 0, or when the denominator approaches 0, it tells you that the Fa maximum approaches infinity. So let's solve for the denominator equal to 0. So to say the denominator equals 0 means that 1 is equal to mu s times tan theta, Okay, now what is mu s? We're going to use a little bit of trig here. So mu s is tan of the static critical angle. So that's tan theta s times tan theta. Okay, and then I think we want to flip this over. So that tells us that tan theta is equal to 1 over tan theta s. But 1 over tangent is cotangent. Cotangent of theta s. And the cotangent of theta s is the same as tangent of 90 minus theta s. So these are some trig identities that I don't expect you all to know these particular trig identities, but I sure hope you can look these things up and work with these sorts of things. 90 minus theta s. Okay, so now this is really interesting. So it's saying that this denominator goes to 0 and the applied force can just go to infinity. You can push as hard as you want and that thing will never slide up, will never accelerate up. If the angle theta is equal, so tan theta is equal to that, or theta is equal to 90 minus theta s. So if theta is equal to 90 minus theta s, or of course steeper, so if theta is bigger than or equal to 90 minus theta s, then the maximum applied force is just infinite, equals infinity. Okay, so this is really cool. What could that possibly mean? So first of all, let me just show you that there should be something like this happening, just sort of obviously. Okay, so if we make the angle big enough, like crank it right up to 90 degrees, then it's obvious that no matter how hard I push horizontally, there's no way this can start accelerating up. Okay, but what this thing is saying is it doesn't need to be as steep as 90 degrees. You can actually crank it back a little bit and still apply an infinite force and this thing not accelerate up. That's surprising, and that takes a little bit of thought. Okay, so let's see what this thing is saying. What it's saying is this. Suppose that the critical angle is like 30 degrees. Yep, when I crank this thing up to 30 degrees, that's theta static, and it starts to slide. Okay, so we'll draw the picture over here. So this is, say, theta static. Let's say it's 30 degrees. If we crank it up to that angle, then it will begin to slide. So then, but we have theta is greater than or equal to 90 minus theta static. 90 minus 30 is 60. So this is about 60 degrees, is something like this. Okay, so if we crank our incline up to 90 minus theta static, okay, then what it's saying is that I can apply a horizontal force to that thing that is just infinite. Okay, so clearly that's true when the angle is 90, but I can crank it all the way back to 90 minus theta s and still apply an infinite force and it won't accelerate up. So that's really cool. So that when I solved that thing, when I did that, it was like, whoa, that's weird, that's unexpected. And that's exactly how physics works. Okay, so you start with situations that you understand and you just play with them. You add some complexity, you work through the math and so on, and then sometimes things like this emerge. So this is a great problem, so I hope that all of you can sort of work through this. You know, this is a good example of breaking vectors into x hat and y hat components and solving Newton's second law. And also, you know, being careful about your choice of I hat and j hat unit vectors. In cases like this, which are common type Phys 121 type problems, you're looking for solving for fs and the normal, so arrange your I hat and j hat so that one points along n and one points along fs, so you just get one equation and one unknown. 2 copies of that. Okay, so anyways, this was a really cool example, so I hope you liked that example.